Good day to all of you. In today's lecture, we will continue the same ideas that we had seen in the last lecture, namely the isolated power converters. We had seen in the previous lectures that in switched mode power conversion, we defined a basic cell which consists of a single pole double throw switch and one energy storage element inductor, and then this was converted in several ways to identify different power conversion functions, namely buck power converter. Then we saw the boost power converter, then we saw the buck boost power converter. So, all these power converters were providing power from a source to a load with the ground potential which is common, the zero potential which is common for the source as well as the load. So, such converters were called the non-isolated power converters, and this is a non-isolated buck converter, and we saw the variations of boost converter and flyback converter, all belonging to the non-isolated family of power converters. And then in the last lecture, we introduced the idea of isolated power conversion, and we had seen that the isolation is obtained by an electromagnetic process of decoupling the source side potential and the load side potential. If the source is at certain potential, if the load has certain other potential, both of them are electrically isolated at the transformer which provides electromagnetic isolation. Power is converted, energy is transferred from electrical to magnetic and then magnetic to electric, achieving electrical isolation between the source and the load. And in the last lecture, we saw the key idea of this isolation is through an electromagnetic process which is through a transformer which is connected to the source side on the primary, the source side on the primary and load side on the secondary. And in that, the important point to notice is that the electromagnetic element should have the flux operating in stable condition while this switched mode power converter works. So, for that we saw that the flux balancing required suitable resetting of the magnetic core, and in the whole of last lecture we went through the process of what is known as a forward converter, where the lossy reset, the reset process of the magnetic circuit was being done with losses. This was the forward converter that we had seen in the last lecture, and it introduces a passive method of resetting through a voltage source across the primary, which ensures that the transformer core is subjected to a negative voltage during the off period, and thus the process of resetting got established. And the secondary side voltages, which we notice on this side, AC switching voltage, is then filtered through the inductor L and C, and we provide V naught at the output. The secondary part is identical to our standard non-isolated buck converter. The primary switch ensures that energy is transferred to the transformer primary, and then from the secondary side this energy is transferred to the load. And we saw that we achieved isolation between the source and the load, and the maximum duty ratio, unlike the non-isolated converter, got limited to 0.5 because half the time we needed in order to reset the flux. During the on time when the flux in the magnetic circuit gets established, we needed a similar time in order to reset the flux. On account of that, the maximum duty ratio got limited to 0.5. And the consequence of this is that the magnetic core is utilized only in one side. The magnetization of the core is taking place on one side of the in one polarity. On account of that, even though we are using a material which is capable of getting magnetized on both directions, we are using it in only one direction, and so we say that the core was utilized only to 50% of its capacity. And because the duty ratio was limited to 0.5, the conductors on the primary and the secondary of the transformer carries current only for half the time, and so the utilization of the conductor was also limited to 0.5. And we also saw that during the reset process, double the voltage is applied across the off switch S, and so we would say that the circuit voltage is also only half of what is the maximum voltage which is seen by the switch. So, on account of all these terms, we find that this forward converter, even though it achieves isolation, it loses capacity, or for the same power conversion we have to use a lot more material. Iron is more because magnet is underutilized, copper is more because copper is underutilized. The switches have to be rated for more VA rating because the circuit voltage is only one half, and further there is also an additional magnetization loss. All these points we had seen in great details, and in today's lecture we will see some of these points, and we will see also several other isolated converters. As far as the power conversion, voltage conversion ratio, current conversion ratio, etc. are concerned, we can draw an equivalent circuit where we have a non-isolated equivalent circuit which is subjected to a voltage of Vg into N2 by N1, and rest of the circuit, the L, C and output voltage, all these things are as before. So, we might say that our forward converter consists of a switch plus the magnetization of the transformer, and then as far as the load is concerned, we can treat it as if it is being subjected to a source voltage of Vg into N2 by N1 and a non-isolated converter. So, we will be able to do all the other analysis based on the circuit that is on the secondary side, and the magnetization part alone can be carried out based on the primary side equivalent circuit. The primary equivalent circuit, when the switch is on, the transformer is replaced by its magnetization equivalent Lm, and when the switch is off, this Lm is subjected to a voltage of Vr, which is a negative voltage. So, in this circuit, we could look at the process of magnetization and also the energy associated with the magnetization, and eventually the losses associated with the process of isolation. We can see that as far as the magnetization current Im is concerned, we have replaced the rest of the circuit as an equivalent ideal circuit on the right hand side of this border, and what we have here is a magnetization inductance and a magnetization voltage which normally is realized by a Zener voltage and a diode, and this part of the circuit can be separately seen. So, during the on time, the inductance, magnetization inductance Lm is subjected to a supply voltage of Vg, and so the current, magnetization current is a linear ramp increasing at the rate of Vg divided by Lm is a di by dt, and at the end of the on time there is a peak current reached here which is shown as Im. This peak current is Im peak, and the total energy at that time in the core can be written as 1/2 of Lm into this Im peak whole square. Now, this energy is trapped in the core, and this energy is what we are trying to reset using the process of the reset circuit here, which is the VR plus the diode. So, during the second half or during the off period, the inductance continues to pass this current because the main switch has turned off. This current continues to flow through the Zener, and so during this time we see that the di by dt is VR divided by Lm with a minus sign. So, if VR and Vg are equal, if Vg is equal to VR, then the magnetization time T on will be the same as the demagnetization time, and this is the reason why we are unable to use the forward converter for duty ratios beyond 0.5. So, if we magnetize the core for a duration T on, we will require a similar time for demagnetizing the core, and so the maximum duty ratio at which this converter can be used is only 0.5, and the remaining 0.5 will be used for demagnetizing. So, this is the energy that is in the core, and during the off time that energy is dissipated in VR with this total energy. Integral of the voltage across the reset circuit, current in the reset circuit, and dt, integral 0 to t VR IR dt. By conservation of energy, we can also say that this energy is the same as the half Lm Im peak square energy. So, this energy is what is lost in VR part, resetting part of the circuit, and to that extent this converter will be less efficient compared to its non-isolated counterpart. The magnetization energy that you see here, and this is the energy that is lost in VR, and energy loss per cycle is this half Li square, and this can be replaced by appropriate terms substituted here, and the power loss is energy loss in 1 second. If the switching frequency is f of s, then this whole quantity, which is the energy loss per cycle multiplied by f of s or divided by Ts, is the power loss in 1 second. Energy loss in 1 second is the power loss, and this is a loss per cycle. And if we talk about the power loss that takes place in the converter, this can be modified and put in this form, where half of source voltage, peak magnetizing current, duty ratio, and unit is in watts. This is the power loss, and if we take the ratio of magnetization loss compared to the output delivered, this is more important, because as a ratio this loss will tell us how much is the delivered power and what portion of that, what fraction of that is lost in the magnetization circuit. So, this turns out to be 1/2 of peak magnetization current divided by the load current. If we call this peak current here as peak magnetization current, that divided by the load current is multiplied by 0.5, and that gives us the ratio of magnetizing power loss. This loss has to be accounted for. As far as the performance of voltage conversion ratio, current conversion ratio, etc., what is shown here is our equivalent circuit as far as the secondary side is concerned. The magnetic circuit part has been seen already by this section, and the switch non-ideality, what we see here, the inductor non-ideality, which is the resistor of the inductor, the switch non-ideality is the drop in the voltage Vt, Vd, etc., and the source non-idealities, which are again resistance of the source, etc. All these may be evaluated by analyzing the non-isolated equivalent circuit, just as we did in the previous circuit. And the loss in the magnetic circuit can be separately analyzed by this simple idealized circuit, where the magnetizing inductance is charged by Vg and discharged by Vr. This is a fairly simple method of doing the complete steady state analysis. And we saw that the loss on account of magnetization is 0.5 times peak magnetization current divided by the load current. Normally, we would like to keep the peak magnetization current approximately 0.1 times I naught. We will keep the magnetizing current peak to be just about 10% of the load current, and that will result in typical magnetization loss to be limited to about 5%. So, if the converter is ideal and if the magnetization part alone is taken into account, the loss could be 5%. You could have another 5% loss because of the switches, another 1 or 2% loss because of the inductor drops and so on. So, typically efficiencies of the order of 85 to 90% is common. However, this big 0.05 loss on account of magnetization is not good news. So, the next evolution in the isolated converter is what is known as the lossless forward converter. The same forward converter is modified a little so that the magnetization energy is not lost, but it is taken back into the source. So, what we see here is such a circuit which is called the lossless forward converter. What this has in comparison with the previous circuit is that there is a third winding, the primary, the secondary, and then a third winding is introduced in the middle of this, which has the same number of turns as the primary, N1 is to N1 is to N2. So, the middle winding, which is used for resetting purpose, has the same number of turns as the primary winding, and the secondary winding has number of turns N2, which is depending on what is the output voltage that is required. So, there is an additional winding number 1, and it has a 1:1 turns ratio number 2, and the purpose of this winding is to return the magnetizing energy to the source. So, these are the 3 crucial points in this. Let us see how this happens. If we see the magnetization reset portion alone, we have 2 windings N1 and N1. Winding 1 and winding 2 are having the same number of turns and they are tightly coupled. The reset winding is tightly coupled to the primary. This means that there is no energy leakage between the primary winding and the reset winding. This IP is the primary current, IR is the reset current, and Vp is the primary voltage. So, when the switch S is on, the primary voltage is Vg in the positive direction, and thus that results in the flux increasing linearly to reach a maximum flux of phi m. We might call this as phi m. So, as soon as S is switched off and it is moved to S bar, what we see is same Vg is now applied across this winding, same Vg is applied, but with a sense which is totally opposite. Dot of the winding is now at the bottom in comparison with the top, or effectively we are applying minus Vg to the winding. So, we are applying a voltage which is exactly the opposite polarity of the source voltage. So, if we find that the flux during the on time was increasing linearly in the positive direction, during the off period, the winding is now subjected to a voltage of Vg, but with a negative polarity. So, naturally the flux starts dropping, and in an equal time as the on time, the flux will reach at a value of 0 and the flux would have completely reset. We ensure that this S bar is made of a diode, so that the current will not go in the opposite direction and flux also will not go in the opposite direction. So, the process of resetting is now being done with another winding, and the reset energy is going back into the source Vg. During this period, this entire reset energy is going into the battery, which means that we have recovered completely the magnetic energy and there are no losses in the converter. Okay. So, during the off period, when the switch is connected to S bar, you can see that the magnetization current IP, which had reached a peak current, just transfers to IR. Now it flows through IR back into the source in the opposite direction. So, what we notice is that the flux is now being reset. There is a negative voltage across this winding, and this negative voltage forces the current back into the source, so that this current falls all the way down to 0. This, as I said, the reset winding is tightly coupled to the primary winding. So, this winding is normally called bifilar winding. The two windings N1 and N1, the reset winding and the primary winding, are wound together with a turns ratio of 1:1 with the same number of turns, but only with the sense being different. The primary has dot on the top and the secondary has dot at the bottom. So, the reset winding carries only in the previous one we must have seen, this reset winding carries only the reset current, the magnetizing current, and so there is no need to make this winding capable of carrying the full load current. It will be wound only for carrying the magnetizing current, which means it will have a very small cross section, and so practically it will occupy very little space. The transformer space, copper space, is decided mainly by the primary and the secondary, and the reset winding will occupy very little space in the transformer, because it handles only the magnetization current, and the magnetization current is a small fraction of the load current. The circuit realization, you can see, of this S and S bar is done by a transistor, MOSFET or a bipolar transistor. S bar is realized simply by a diode, because this stored energy in the inductor will force the current through the reset winding and through the diode, and this current has to flow only till the current reaches 0. So, a simple passive diode is used for this switch. The secondary part is just as before, just like a non-isolated converter. So, this type of forward converters are called lossless forward converter, compared to the previous one, which was a lossy forward converter. The flux reset voltage in this is because of the reverse connection of Vg to this winding for the appropriate dot positions here. You can see during the positive half, plus voltage is applied to the winding and flux is increasing in the positive direction, and then during the negative half, during the reset interval, the voltage across the winding is negative, and so flux starts decreasing, and because of the diode in the circuit, the current does not reverse in the winding and flux also does not reverse in the winding. That is the process of reset. The secondary and primary current can be separately treated by completely transferring the reset process to reset winding. Now, N1 and N2 are the primary and secondary windings, and you can see, if you assume that IL is constant, then the secondary current is a square wave current. During the off time, it will freewheel through the freewheel diode. During the on time, it will flow through the mains diode here S, which will also flow through the secondary winding, and then a reflected current of this IS plus the magnetizing current is what will be flowing on the primary. This part is the peak magnetizing current, the rest of it is the reflected primary current, and this is how we will see the primary and secondary current in the windings. Now, if you see the reset winding, just when the switch is turned off, the magnetization part of the winding will get transferred to the reset winding, and it will slowly die down in a time which is same as the on time to 0. There, during this time, this reset current is completely being transferred to the source. So, if you see the source current will show the secondary reflected current on the primary plus the magnetization current, but during the reset period, the magnetization current reverses direction and it is flowing back through the IR winding, through the diode, it flows back into the source, and that is what you see here. So, practically the current that is fed back into the source is the same as the current that was taken for magnetization, and so ideally the entire magnetizing energy is going back into the source, and so the converter does not incur any loss on account of magnetization. The source current takes this magnetization current back and puts it into the source. Okay. So, here is a picture of the complete set of waveforms. You see that the flux in the core on this side and the primary voltage, which is both positive and negative in the on period and the reset period, the secondary current which is on only during the on period, and the primary current which consists of secondary reflected current plus the magnetization current, and the reset current which is only in the off period, also part of the off period, and which is the same as the magnetizing current, and the source current which is the primary current during the on period and the reverse of the recovery current, the reset current during the off period. This is the complete set of waveforms on that converter, and the highlights of this are that all other things being same, reset is now lossless. To that extent, we get better efficiency. However, the duty ratio is limited to 0.5. So, this negative feature remains as before. Core utilization is only 0.5. This negative feature also remains as before. Conductor utilization is 0.5 because the winding carries current only for half the duration, and circuit voltage is also 0.5 because during the off period the switch experiences double the source voltage. So, switch has to be rated for double the voltage. So, all these negative features remain as it is, but we have now achieved lossless reset, and this is our original purpose, isolation between V0 and Vg, and now with lossless reset it is now being done efficiently, but there are a number of limitations. The core utilization is not perfect, conductor utilization is not perfect, circuit voltage is also double, maximum duty ratio is only half, and so on. There are a number of other circuit configurations which achieve the same lossless reset and also achieve isolation, but with reduced penalty in terms of material utilization. This is another variation. This is called a lossless 2 switch forward converter. What you notice here is that the winding has only, the transformer has only 2 windings, but we have added 2 more diodes, 1 and 2. So, when the main, and we have also put 2 switches S and S. So, when the switches S is on, initially the transformer is supplied power from plus and minus Vg, and the magnetizing current is building up on the primary, secondary voltage is induced, and then secondary part works as before. But the moment we switch off S and S, what we notice is that through the diodes that are here, negative is connected to this end and positive is connected to this end through the diodes, or we apply minus Vg to the winding during the off period, and this entire reset process is now done by the same winding and sent to the same source. What we have saved is the additional winding that was added in the first converter that we had seen. Okay. The process of core flux increasing during the on time, decreasing during the off time, and the winding voltages, these are very similar to what we have seen before. What is seen here is core flux and the primary voltage. The secondary voltage and the reflected secondary voltage are also identical, but now the primary itself carries the reset winding, reset current. You can see that the primary winding was carrying the magnetization current, and when the switch S and S are switched off, the same current comes from the negative bus in the same direction here through the positive diode, it goes back into the source. So, primary current now resets through the same winding by applying a negative voltage. And if you see the source voltage, during the on time, the primary current is the same as the source current. During the reset time, primary current is the inverse of the reset current. On account of that, you see the source current is in the negative direction. Just as before, we see that same amount of energy that was drawn during the magnetization part is being sent back to the source during the demagnetization part. So, we have efficiently, without loss, we have recovered the entire magnetizing energy, and so this isolation is now without any penalty on efficiency. So, now the maximum duty ratio continues to remain at 0.5, the magnetic core utilization remains at 0.5, the conductor utilization also is only at 0.5, but because of the diodes here, now we do not see double the voltage on the transformer or on the switch, but there are two switches now. Instead of one switch, we have two switches, but the circuit voltage is now 1 and reset is lossless and isolation is achieved. So, what we have now, we are trying to find out circuits which one by one get better and better for the required performance. Isolation is our main goal. Initially, we had a lossy reset, now we have a lossless reset, then we had a circuit voltage which was double, now that also has come within normal utilization. Now, we have in this configuration, we have three other limitations. Duty ratio is not full, magnetic core is not fully utilized, conductor is not fully utilized. You will see in the next few slides other circuits which are doing this better. The next circuit that achieves this isolation is called push-pull converter. You can see that this push-pull converter is just two forward converters put back to back. For example, this winding 1 and this top half forms one forward converter, and then winding 2 and the bottom half forms the second forward converter, and both these forward converters are interleaved in the same transformer by two switches here. So, we will see the waveforms now. So, effectively push-pull converter is really two forward converters connected back to back using the same magnetization circuits. The transformer is the same. Earlier we had a circuit where winding 1 and winding 1, the positive part and winding 1 made the one forward converter, and here that is retained, and we have put one more winding and then a negative part of this here with respect to the center tap. So, effectively now two forward converters are integrated into a single magnetic element. Switches turn on now in alternate half cycles. In one half cycle, forward converter can work only for 50% of the duty ratio. So, in the first 50%, one forward converter is working, and in the second 50%, the second forward converter is working. So, effectively the load will be receiving power in each of these half cycles. So, we find that the duty ratio on the secondary side, as far as what we see on the secondary side, is really 100%, even though each half of the primary switches operate at the most at 50%. So, we will see because of this the duty ratio can go to 1, that one of the limitations of this isolated circuit is overcome. The primary switches continue to be at 50%, and these two alternate half cycles make sure that the magnetic core is energized in direction 1 in one half and in direction 2 in the other half, and that ensures that the magnetic core is magnetized in both positive and negative halves. On account of that, we will find that the core is also utilized fully in both directions. So, the switch S1, call this as S1 and call this as S2. S1 and S2 are turned on as per the duty ratios that are shown here. S1 is turning on in alternate half cycles, S2 is turning on in the other alternate half cycles. So, what we see here are the switch duty ratios. On account of this, when S1 is on through the positive half of the secondary, voltage is applied to this inductor and you see that the current is rising. This is the first part. Current in the output inductor is rising. Then when the switch S1 and S2 both of them are off. So, this is the interval when both are off. S1 is also off, S2 is also off. So, during that time the output inductor current is just freewheeling through these two diodes and through the secondary winding. It freewheels like this and like this. Both diodes are on and they are adding up to the inductor current IL. So, primary side none of the windings are conducting, both the secondary windings are carrying half of the load current. This would be the current during the period when both the switches are not conducting. And in the next half cycle, it is the S2 which is conducting, and again on account of that, through the bottom winding of the output transformer, through the bottom diode, inductor current is now increasing. So, effectively if we find out what is the current in I plus and I minus, so during the active regions the current will be the same as the output current. What you see here in the circled, but during the time when both the switches are off, in fact I plus and I minus will be equal and opposite. The entire load current will be shared by both of them and the freewheeling will take place through the winding and through the diodes. This will be the secondary currents. What you see here are the secondary currents. The switch currents are the secondary current reflected onto the primary side. So, IS1 carries current. Current in S1 is whenever S1 is on. Current in S2 is whenever S2 is on, and in between during the time when both of them are off, there is no current in either S1 or S2, but the load current is supported by freewheeling through both the diodes and the secondary winding, and primary currents are totally 0. Right. How about the transformer voltage and flux? So, during the time switch is on, the transformer is subjected to a voltage which is positive for that winding. During the time when both switches are off, the transformer has no voltage, and during the time when S2 is off, the transformer, because of the dot points being different, transformer is subjected to a negative voltage. So, you see that the voltage applied to the transformer is perfectly symmetrical, the positive half and the negative half are equal, and so the flux will be now swinging both in positive direction and in negative direction equally, and so we will see that the core is utilized better in this. But there is one catch here. Supposing if the voltage is perfect and the durations of positive T on positive and T on negative are also perfectly equal, but if the switch voltages, switch drops VT1 and VT2 are not equal, then we will see that there is a net DC voltage applied to the winding of the transformer, and this transformer core can saturate. This is something which requires suitable handling, and we will not look at it right now, but later on we will see this when we try to do the current mode control. One of the negative points, one of the dangers of push-pull converter is that it has the hazard of core saturation, and so at low powers it can be directly used. At high powers you have to take additional precautions to make sure that the core does not saturate. So, let us see how the isolation and all the penalties come about. What we want is isolation, and here also the reset is without loss. Duty ratio is now 1, because as far as load is concerned, we can pump power practically continuously at 100% duty ratio. The core utilization is also now full, both on positive and negative. The conductor utilization is only half, because each winding carries current only for half the time. Either winding primary 1 and this winding, or the primary 2 and secondary the second half of the center tap winding. So, this continues to be a negative point, and then the circuit voltage is still 0.5, because whenever one switch is on, the other switch is subjected to double the source voltage. There is another negative aspect, which is the hazard of core saturation. At low power, this is not very significant. When you are handling small powers, this is not a significant point. So, we have practically now overcome full duty ratio problem, full core utilization and lossless reset, but there are two other issues which are conductor utilization and circuit voltage. Okay. So, let us see what are the other circuits. The next, the family of isolated converters has a few other circuit topologies. Out of them, this half bridge and full bridge are the important converters which are used for large power ratings. Full bridge is practically the only circuit which is used for very large power ratings. Isolated flyback power converter is used for very small power ratings. This is for small, this is for big, going even into megawatt of power, and this is for medium, hundreds of kilowatts or hundreds of watts, few kilowatts, tens of kilowatts and so on, but big power is handled by full bridge converter. Very small power, less than 100 watts, and that kind of power is handled by isolated flyback converter. And then the medium level of power is handled by half bridge converters. So, let us see how these circuit topologies look like. You can see that this half bridge converter utilizes two switches, but unlike the two switch forward converter, these two switches are operated in the push pull mode. That is, for in one half cycle, the top switch is pulse width modulated, in the other half cycle, the bottom switch is pulse width modulated. If I call this as S2 and this as S1, S1's on time is controlled in one half cycle and S2's on time is controlled in the other half cycle. And the isolation transformer is now connected between the switch and the midpoint of Vg. This is obtained by splitting Vg using two capacitors. So, that this midpoint will be Vg by 2, and then it is, we will just in a moment see what this Cb is. This is called DC blocking capacitor. We will see the function and value of that. So, this power is connected, this midpoint is connected to the other end of the transformer. For a moment you assume that the Cb is short circuit. Later we will see what are the design conditions required to satisfy that. So, in such a case, the transformer primary is subjected to half the supply voltage when the top switch is on with positive polarity. So, we will say that in one cycle, when top switch is on, the transformer is subjected to Vg by 2, and when both the switches are off, transformer has a voltage of 0, and when S2 is on, transformer is seeing a voltage of minus Vg by 2, and then during this time when both are off, it is 0 again. So, you see that a perfectly symmetric square wave is applied to the transformer, both in positive and negative. So, naturally the flux also will follow ramping up, constant flux, ramping down, and then constant flux. So, this will be the flux waveform. So, what we notice is that the flux is now bipolar, or the magnetic core is fully utilized. The transformer voltage is only half the voltage. Supply voltage, if it is Vg, only half of that voltage is supplied to the primary. So, what you will see on the secondary side will be Vg by 2 into N2 by N1 will be the voltage that is supplied to the secondary side, and then you have our standard non-isolated buck converter on the other side. Okay. The Cb has a special function called DC blocking. We will see in a moment what that is. The full bridge converter is using 4 switches, S1, S1, S2, S2. For example, when S1, we will call this as S1, S2, S3, S4, totally 4 switches. When S1 and S4, S1, S4 gives you an output voltage of plus Vg. Then S2 and S3 gives an output voltage of minus Vg. S1 and S3 on gives 0 voltage. S2 and S4 on gives 0 voltage. So, it is possible now by appropriately modulating to get a voltage across the primary, which will be plus, 0 and minus. Now, in a full bridge converter, this is how the pulse width modulation is done to get a square wave AC voltage which is symmetric. And then during the positive half, through the top diode, the load will be supplied. During the negative half, through the bottom diode, load will be supplied. And during the time the voltage is 0, there will be freewheeling of the load current through both the diodes. Now, I have to still explain about this blocking capacitor. So, as far as the secondary part is concerned, Vg into N2 by N1 is the equivalent buck converter's source voltage. Vg star is Vg into N2 by N1. In half bridge, we saw that it is Vg by 2 into N2 by N1. In full bridge converter, it is the full voltage Vg multiplied by N2 by N1, and this is the reason for the name full bridge or half bridge. Half bridge has only Vg by 2, half the voltage only is applied, and in full bridge, full voltage is applied, and this is Vg into N2 by N1. And the full bridge has all the switch S1 to S4 are defined at every point, and at least 2 of them conduct at every instant, whereas in half bridge we have regions where both of them do not conduct. Either S1 is on or S2 is on. We do not have conditions where both S1 and S2 being on, because that will give rise to short circuit of the source. So, there is a region where S1 and S2 both are off. Now, the DC blocking capacitor CB has a very special function. As I said, if the on period of the switches are on or equal and source voltage is certain value, the actual voltage applied to the transformer is supply voltage minus 2 device drops on the positive side, and similarly supply voltage minus 2 device drops on the negative side. And even if supply voltage is very steady, these 2 voltage drops need not be what you drop here drops, and then similarly on this side the device drops need not be perfectly equal. So, on account of that, it so happens that the positive area of volt second and the negative area of volt second will not be equal in any application. There will be a net DC voltage, and the purpose of this CB is to block that DC voltage, and it is called DC blocking capacitor CB. It blocks the DC voltage from reaching the transformer and saturating the core. How do you size this capacitor? We have to make sure that the voltage across CB is very small, and it is only to block the DC voltage that will be across the transformer. And the voltage across the capacitor is very easy to find out, because in every half cycle of Ts by 2, the primary current is flowing through the capacitor. In one Ts by 2, it flows in one direction, in the other half it flows in the other direction. So, what we notice that in every cycle, this is the total charge that is going into the capacitor in the positive half, and the same similar kind of charge Ts by 2 into minus Ip flows through the capacitor in the negative half cycle. So, this divided by the capacitance, the charge divided by the capacitance will be the voltage on the capacitor delta V. So, if this blocking capacitor should not have any consequence on the overall voltage applied to the transformer, then this delta V has to be very much small compared to supply voltage, and that is what this equation tells. The ripple voltage on the capacitor IT by C, IP multiplied by Ts by 2 half the period, this is the Coulomb charge into the capacitor. This is the blocking capacitor value, charge by the capacitance is the delta V or change in voltage in the capacitor. So long as that is very small compared to Vg, the blocking capacitor will do its function well, and that is how the CB is selected. In every application, if I know what is IP and if I know what is the switching frequency, and this is, and if I know how much voltage ripple I can tolerate, then from that we can find out what is the blocking capacitor to be used. Okay. So, now if you see this half bridge or full bridge converter, we can see that isolation has been achieved, duty ratio is 1, core is fully utilized, conductor is also fully utilized, because you see on the primary current is flowing both in positive half and negative half. Circuit voltage is also 1 in the full bridge and half in the half bridge. So, we can see that every one of those negative points which we started with in isolation have been addressed by all these circuit topologies. Okay. But the other performance figures like voltage conversion, current conversion and the non-idealities contributing to efficiency loss and so on, as far as those quantities are concerned, we can replace that isolated converter by an equivalent non-isolated converter. In the equivalent non-isolated converter, the source voltage will be now a function of Vg and N2 by N1. In the case of forward converter, it is just simply Vg into N2 by N1. In the case of half bridge, it will be Vg by 2 into N2 by N1. In the case of full bridge, it will be Vg into N2 by N1 and so on. But the performance of the voltage conversion ratio, current conversion ratio, efficiency on account of the switch non-idealities S and S bar, efficiency loss on account of the inductor non-idealities which is RL and so on, all those analysis can be done in the same way as we had done for the other converters. It is a very similar exercise. Only this source voltage has now been replaced by the non-isolated equivalent voltage, and the circuit is identical to the buck converter. The forward converter, push-pull converter, two switch forward converter, half bridge converter, full bridge converter, all of them have an output LC filter, and in the standard form they all are similar to the buck converter. The analysis of many of these quantities can be done in the same way. The smallest power levels, normally the converter circuit which is very popular is the isolated flyback converter. All that is done is the flyback inductor is now split into a primary inductor and a secondary inductor on the magnetic circuit, and while energizing the core through the primary, energy comes into the core through IP, and then when the switch is turned off, the stored energy in the inductor goes through the diode to the load. So, this also is a fairly simple converter, and the important point to notice is it has only one magnetic element for both isolation and storage. In the earlier converters like the forward or any of them, we had one inductor for smoothing the energy flow and another electromagnetic circuit for providing isolation. So, there are two electromagnetic elements, but in the flyback converter, these have been combined into a single electromagnetic structure. This is working both as a transformer and also as an output filter. So, the inductance of the flyback, non-isolated flyback is seen from the secondary side inductance, but energy drawal is from the source from the primary side inductance. You can say that this inductor has LP and LS. LP will be proportional to NP square and LS will be proportional to NS square. So, this circuit also can be found out. In this again utilization is not as good. Magnetic core is utilized only in one direction because it is not a transformer, it is an inductor. Conductor is utilized only for half because the winding carries current only for part of the cycle. Duty ratio probably can go a little beyond 0.5, normally typically up to 2/3. Circuit voltage also is only partly utilized. And because of these reasons, because of these limitations, the flyback isolated or isolated flyback converter is normally used at low power levels. At very low power levels, this is practically the de facto circuit topology, because this is the simplest one with only one electromagnetic element and then a capacitor and the output resistor. At small power levels, this is the most economical circuit design. Okay, now let us see again the bridge converters. At very high power levels, it is half or full bridge. At medium power levels, it could be single switch forward converter or the isolated flyback converter. At very low power levels, it could be isolated flyback converters or the lossy forward converter, because at low power, you do not care very much about the losses. Another interesting thing is that in the half bridge circuit and the push pull circuit and the lossy reset or lossless reset, you find that there is energy trapped in the core in the form of magnetizing energy. In the push pull circuit, it is true because there are conditions when both the switches are off. In a push pull circuit, not push pull, in a half bridge circuit, you can see that there are instances when both the switches S1 and S2 are off, and at that time if there is any trapped energy inside the core, it has no place to go. So, naturally it will create problems in terms of over voltages, etc. Half bridge circuit has this kind of trapped energy. The same is true in push pull circuit also. When both the switches are off, you have no conducting path, but there could be trapped energy in the core. In the forward converter also, if the lossless reset or lossy reset or lossless reset, whichever is used, there is a trapped energy in the core. We know that energy trapped in any circuit can give rise to problems if we do not have appropriate methods of absorbing that energy. From that point of view, the full bridge converter has no trapped energy, because any time at least two switches are on. So, there is always a path for the magnetic circuit to complete its current. That is one reason why full bridge circuit can be scaled to any power level, to megawatt power level also. The same is true with a two switch forward converter. There also there is no trapped energy. The same winding through diodes will completely transfer its energy to the source, and so this two switch forward converter and the full bridge converter in a way are circuits which can be used or scaled up to any power level. So, that brings us to practically the end of non-isolated converters, the different circuit topologies. There are many other circuit topologies, but in principle this should give rise to most of what we want to do a little later, and we will see later several circuit examples of the same type of converters. I just want to briefly indicate what is going to come next. See, in all these converters, what we see in a canonical form is a buck converter or a boost converter or a flyback converter. In these converters, there is a diode which is in the circuit, and this diode does not allow the current in the inductor to be in both directions. For example, if the current in the inductor is like this, diode can support it, but if it reverses, the diode cannot support. So, in all these converters, as we realize with a transistor and a diode, there is a problem relating to the flow of the current in both directions, and that gives rise to a new operating mode called discontinuous current mode of discontinuous conduction mode of operation.